Hello, welcome to the Cognitive Science Colloquium for February 3rd, 2025. In 1982, when I had just arrived at the University of Chicago, I met in the halls of Gates Blake, David McNeil. I was brand new, and he said, the linguistics department needs you to give a talk. I said, oh, that's great, because I felt so great that I was going to give this talk. And so I did. I had worked on a dissertation at Berkeley, where some of the best advice came from Chuck Fillmore, Frames, which you'll hear about today. So there's a lineage here. And it was on things like the linguistics of what's now called the XYZ construction. Things like causation is the cement of the universe, or death is the mother of beauty, title of my first book, quote from Wallace Stevens. And I was so jazzed to give the talk, I gave the talk. And people who didn't seem to be related to David McNeil at all were filming the talk. They wanted to know. These were the days when you had to approve that they could record. Now everybody everywhere records. And I realized afterward that the reason they wanted me to give the talk was so that they would have my co-speech gestures without my being compromised by knowing that they were really going to study my gestures. So then I went right in the lab and looked at what everybody was doing and got to know all these people. And I was extremely impressed that whereas my dissertation had all been on language, they were working multimodal. And of course, they were working with both language and gesture, but they were quite aware of material affordances and the environment, paralinguistic elements, the full range of multimodality in human communication. I was also impressed with how hard they worked. They did a ton of hand tagging, annotating in the dark of night. This little inflection, that little beat, this little thing, and all this data. And they didn't even actually seem to realize that all around the world they could send this hand tag data out. And later on, I got to know about Elan and this platform on your laptop for very carefully annotating everything. But I was a computer guy. I was a symbolic AI guy who was just learning about parallel distributed processing because I'd spent a year at San Diego. I thought, wow, we need to get some computers in here. Well, now fast forward to our guest today, Marcelo Viridiano, who is a product of FrameNet Brazil, where they have a computational linguistics lab. He's a postdoc here this year, and his dissertation was on building a massive data set that is multimodal and multilingual based on frame semantics, as a lot of the work I did was, but now exploring and pushing the boundaries of using computational and synthetic agents to help tag, clean, organize, and in fact, analyze the multimodal data. So he's going to speak today about the research that's ongoing, hot out of the oven. Here it is. A splendid time is guaranteed for all. Multimodal research in vision and language, emerging trends and the role of frame semantics with emphasis on emerging. Please help me welcome Marcelo.
Can you hear me from the back if I speak like this? Okay, yeah. So there's this thing in movies that we call exposition that we usually don't let actors say things that they're going to do. We expect them, the audience, to understand what's going to happen during the presentation. But since I'm in that situation that you see on memes, like, yeah, when you see like a freeze frame and a scratch, a distance, like, yeah, that's me. You might be wondering how I end up in this situation. So yeah, I end up in this situation because of a conversation I had with Mark on November last year. He invited Fred and I to come here to talk about the research we were doing. And the first thing that came to mind is how could I make this, first of all, not boring, in the sense that when you're presenting your work in conferences, that is usually one person, hopefully just one, but sometimes more than one, that raise their hands after you're finishing your presentation. And that's, hey, yeah, great work, but have you considered using the exact same thing I'm working on now? Just, it's not a question, it's just more of a comment, like, amazing work you're doing, but yeah, have you considered using my work? Yeah, that's the kind of thing that I'm trying not to do today. So eventually I will do things like, oh, you're working on fact checking. Yeah, did you consider working on frame semantics? Because we can do that. So there's a bunch of things that we can do with frame semantics, but my idea here is how can we do this not boring while providing some kind of help for the project you have to do here. So hoping this will be a mix of the research I did through my PhD, what I'm doing here, but providing some papers and tools that you can use with whatever projects you decide to do this course, right? So here's my idea. Mark and Fred talked about this idea of theories supporting the building of models, and then models enabling you to build tools to work, and how that correlates with the theory being helpful to identify some kind of problem, and the models to test the hypothesis, and your tools to propose a solution for that problem, right? The idea here is, what can we put here in the middle of those things? Because that's what you're doing now, right? So you're trying to find some research that you can work on, and while researching that topic, you would like to find a gap on the research, and you like to build a project on top of that gap that has some like timetable and some milestones for the project. So what we are doing here today is trying to find this. While discussing what I did during my PhD and what I'm doing here, like for my postdoc, how can we go through the research in a certain field, and how that research leads you to find a gap in the research, and how that gap can become a project. So that's what happened with my PhD, and that's what's happening now with my postdoc. I found a gap, and I'm working on a project. So one final note, sometimes you will see slides with more text. I usually don't do that. I like to talk on top of slides, but sometimes you'll see slides with more text. It's because this presentation is already available to download. So when there's a lot of text, it's just because you can have some context and not just an icon, and you have to go to the video to know what I was talking about. So I have more text on the slide so you can just read the slide later. Okay, now let's start the presentation. So my name is Marcelo. I'm a PhD in linguistics, working on multimodal approaches in the field of frame semantics for automatic processing of combined image and text data. This is the long description for this. I'm working on this intersection of multimodality, machine translation, and frame semantics. So both the project I did during my PhD and what I'm doing now happens on the field that intersects multimodality, machine translation, and frame semantics. During my PhD, I worked developing a couple of data sets and analyzing data sets mostly because I was trying to build a data set from my PhD. So I built one data set, but I also worked on the development of the CDQA data set and the Shades data set. And of course, the data set that became the result of my PhD dissertation, which is a frame-based multimodal multilingual data set. There's a bunch of names there because that's a project from our lab. So we have a bunch of students working on that and the paper. So everyone is mentioned on the dissertation. The context for today is this, that deep learning and its applications have driven transformative research and development across a wide range of real-world data modalities. And we are seeing an increased interest in the intersection of vision and language. That's happening not only with data sets, but also with AI. So today we're gonna approach this topic in 3 steps. First of all, I'll give just a quick overview of the research in visual vision and language. And we are going to explore a few tasks and data sets that are part of this research on vision and language. And then I'll discuss what we did on FrameNet Brazil, what we are doing now to address the issues that we find on the tasks and data sets that we have. So you may see that this is a paper that I borrowed the title for this presentation, which is a great way to start if you're going to do anything using vision or language combined. This is a survey from 2020, and it has all sorts of generation tasks and classification tasks and retrieval tasks that you can do within the field of vision and language, pointing to the data sets that are used on those tasks, and papers that provide analysis for each of those tasks. So if you're building anything that combines vision and language, I would recommend starting here, right? And you have the paper on the syllabus to check. Some of the tasks that interest us in FrameNet Brazil are tasks related to visual semantic role labeling, which is the identification of participants of a situation. Image captioning, which is like generating descriptions for an image based on a data set, and multimodal machine translation, which is specifically what I work in my project. So for that, you can see like you can use, and I promise this is going to be like just a few examples, like how you can use FrameNet, for example, for routing semantic roles in images, or how you can use, for example, generated an image caption using FrameNet, right? So while looking through that paper, you will find something interesting regarding the type of data or data sets that they use for the task. And let's look through that. First of all, via the multimodal data sets that are used for those tasks. If you go to the table that talks about the image caption research, you have a list of papers. So the numbers referenced, the reference there is for the papers are working on those tasks. And what you can see here is that most of the papers are using the same data set, the Microsoft Colloquium data set. It's a huge list of tasks using the same data set for image caption. The Microsoft Colloquium data set is a data set for object segmentation. So what you have is a bunch of classes, 80 classes. And for example, if you choose pizza here, you get images like this. And by the way, COCO means common objects in context. So you find objects like pizza in the context where pizza is usually appears in it. So you have this image, but you also have what they call the semantic segmentation, which is this image around the pizza, and you have the objects that you have on this image, and you also have descriptions for that image with the segmentation. And this is what they use to train models to try to identify objects in images that are not part of the training set. So you show the model a bunch of images annotated like this, with the classes annotated and the description of what's showing up here, and you would hope that the model will identify whatever you're showing them there. For multimodal machine translation, we have the same thing. Most of the tasks that work on multimodal machine translation are based on this data set called Multi-30K. And Multi-30K is a data set that is also composed of images, and you have the descriptions of the image in English. So this was crowdsourced. A bunch of people on Amazon Mechanical Turk describe those images, but you also have people working on the expansion of this data set. So you have not only English, but you also have descriptions in German, French, Dutch, Japanese, Chinese, and what was part of my research, expanding this data set to Brazilian Portuguese. So now You have the image, the descriptions in English, and all those languages, including Portuguese. This was the research part of the project. So the thing is, when you do the research, you start finding not only the data sets, but a bunch of people criticizing those data sets and finding problems with those data sets. So the problem we find with most multimodal data sets are about bias in the data sets due to ill-considered data set creation practices, which is someone saw the image and wrote image captions for the data set, but no one took the time to go back to the image and check if the way the images were described had some sort of bias or ethical issues. There is also the problem of perspective in data sets. So most of the time you have just one perspective because they try to do that thing called inter-annotator agreement. So if someone is describing an image in a different way, they try to take that off the data set, which is something that's being criticized. So those data sets are from 2017, 2016, and now because of the way those data sets are being used in machine translation tasks and for training models, they're starting to see a bunch of issues with those data sets because the bias that was inserted in the data set during its creation are now showing up in the machine learning models. And also problems with how the meaning is represented in those data sets. Because there's this idea that if you are looking to what's just the surface level of the description, you cannot extract meaning from that unstructured data. So just looking to the descriptions, what you can extract are the entities that are part of that image, but not specifically the meaning of what's happening there. So how this affects AI. As I said, there's a paper like from Emily Bender, which is very vocal on this thing of you cannot extract meaning from the surface level, criticizing the way data sets are used for trained machine learning models, and also the problem of scaling laws for neural language models, which is something more complex, but I'll give you just a hint of like a 2 minutes clip of a video. You can watch the video later, it explains to you detail, but for the purpose of this presentation, the first 2 minutes will be enough to help you understand what I'm doing. So.
AI models can't cross this boundary, and we don't know why. As we train an AI model, its error rate generally drops off quickly and then levels up. If we train a larger model, it will achieve a lower error rate, but requires more compute. Scaling to larger and larger models, we end up with a family of curves like this. Switching our axis to logarithmic scale, a clear trend emerges, where no model can cross this line, known as the compute optimal or compute efficient frontier. This trend is one of 3 neural scaling laws that have been broadly observed. Error rate scales in a very similar way with compute, model size, and data set size, and remarkably doesn't depend much on model architecture or other algorithmic details, as long as reasonably good choices are made. The interesting question from here is, have we discovered some fundamental law of nature, like an ideal gas law for building intelligent systems? Or is this trend just a result of the specific neural network-driven approach to AI that we're taking right now? How powerful could these models become if we continue increasing the amount of data, the model size, and compute? Can we drive errors to 0, or will performance level off? Why are data, model size, and compute the fundamental limits of the systems we're building? And why are they connected to model performance in such a simple way?
The important question that you extract from this brief 2-minute clip is that how powerful can these models become if we continue to increase the amount of data? So we just keep feeding the models data. That's what's happening now. Each week you see like a model with 700 billion tokens, and you keep feeding uncurated data. And the problem is, we know already that the range of repetition frequency leads to a severe degradation in the model performance. So we are plateauing the performance of those machine learning models. With all that said, I have a few things that are going to be the lens that you use to see the research we are doing at Frame Brazil. So there's a few conclusions that we can extract from what we've seen so far, and a few predictions. The first thing is, just as there was no reason to believe GPT-4 or O1 was the absolute hard limit, GPT-3, GPT-03 is not the hard limit, but there's definitely diminished returns at scale. So as the models, you had a jump from GPT 3.5 to 0.4, a smaller jump for O1, a smaller jump for O3, and the return that you get for those models with the amount of data you input is not inequally. At some point, rather sooner than later, bigger models alone won't give us that much of qualitative improvement. And we still have a lot of room for improvement in scaling down models, making efficient versions of today's models that can run on commodity hardware. And the predictions that we can do from that is that when it happens, domain-specific and human-curated data will play a crucial role. And also, at some point, anyone will be able to fine-tune GPT-4 on a 300 GPU at home on domain-specific data. And funny enough, when I was working on this presentation, you can like this happened between when I wrote this and today, because right now, like we have Sky One running on a $450 block term. So when I wrote that, now this is happening. So this is not future anymore like it. And a part of we still have to see how the thing is working with the Chinese models, but most likely you can do that. What they're calling distillation with it's just a way of working on curated data. And the thing is that we believe that multimodality is the next frontier. Audio and visual is only the beginning. So we have like multimodal models for things like health. So you can have like 4D Braille scans for multimodal data. So with that in mind, let's talk about what we are doing at Frame Brazil, what I did during my PhD, and what we are doing now in Brazil, which is about the gap that we found on the current data sets and how we plan to use FrameNet to fill that gap. So the idea of the semantic gap is something like this. Imagine you have this image and you have this line here, which is the difference in performance in identifying the components of an image and their relationships to determine the overall meaning of the image. So at one point you have like no idea what this image means, and at the other extreme, you have full understanding of what's happening in this image. If you get an image like this and give it to the Microsoft computer vision model, what it will do is to detect entities and objects in the image, and using a bottom-up approach, try to build the relations, trying to build the relations based on a construction. So it sees the images, and based on those images, it starts to creating relations for those images. So you see like a close-up of a man's face, a man and a woman sitting together, a close-up of a person's mouth. That's just a bottom-up approach. You identify objects here, identify the entities in an image, and try to build up sentences up from those relations, right? You can also extract like a JSON file with the coordinates of the bounding boxes and etc. So let's say this vision model performs like this, right? If you give the same image to ChatGPT-4o, it will give a description like this. So the image captures a close-up moment between two teenagers engaged in conversation, a young man wearing an orange hoodie, so on and so forth. The difference here is this part. ChatGPT instead of just figuring out the entities in the image, is also trying to figure out some sort of event that's happening in that image, based not only on the entities, but on how the entities organize themselves within the image. So let's say ChatGPT performed like this. If you have someone who specifically knows those people, so I know this is Mike, this is Sarah, and this is their first date. This is the position where you have someone that has full understanding of what the image represented, right? So they know the name of the people. But we don't care about this because this kind of information does not help machine learning models. What we care is to reduce the gap between this, what ChatGPT can do now, and how can ChatGPT describe this image as a human, a group of humans who are not familiar with that scene would describe the image, the amount of information that humans can extract from the image by looking at it. And what we try to do with FrameNet is this, to add more information, more granularity to the data in order to move ChatGPT from there to here. So we have a paper for that, presenting the way that we use FrameNet software and infrastructure to address contextual information in both database creation and construction. And of course, what I did with my PhD research was try to reduce that gap by providing more information to machine learning models. So let's talk about Frame Multi-30K, which was the result of my dissertation. And before that, I promise it will be fast, but we need just to recap the framed part of Frame Multi-30K. I promise you, this will be framed in 60 seconds. So the idea is, the frame semantics is that approach of semantics where the meaning of words can only be understood relative to a broader background of conceptual scenes or semantic frames they evoke. When you people looked at this image, you know what's happening here. Like you can parse the elements right there and create a description for that image, which will be something like this. In Rome, most visitors visit the gods. So you know. The only reason you can understand this sentence and this image is because in your head, you have a scene that was evoked by those elements in the image and by those lexical items in the sentence. Somehow you know that Rome is a place, that foreigners are tourists, and that the Colloquium is an attraction. That's why you understand what I'm saying here without needing to explain. So tourism is something that people do, they get a plane and go somewhere, like you automatically understand this. And what we do in FrameNet is to model that. So we get that information and turn that into a semantic frame, which in this case is the Turing frame. And we say, oh, a tourist experiences a specific attraction in a specific place, so on and so forth. So we have all those visual elements that you have in an image and all those lexical items that you have in a sentence combined into a frame. That's done. Okay. So how did we do this? Remember that data set I mentioned, the multi-30K that is used for most machine translation tasks? So we got that data set and the expansions of those data sets. So you have also figure 30K entities, which is a different data set, which adds those things called bounding boxes. So you have a description of the scene in English, you have a description of the scene in other languages, but you also have a correlation between the entities in the image and the lexical items in the description. And what we did was to expand that to Brazilian Portuguese, not only by adding new descriptions, but also, which is more important, annotating all those sentences and all those images to FrameNet. So assigning a frame element and a frame to each image, to each entity, to each lexical item that we find in all those descriptions. And what we have as a result is something like this. So you know that the boy, which is the boy in the sentence, is you go by visual activity, which is a person. You have the pool, which is a venue support, and the pool is here. You have all that connected. And since we did that for all those languages, we can now know that those items in Portuguese are also the same frames and frame elements of those items in English, and all that is connected to those pixels in each image. So that was my PhD. What am I doing now here? The idea now is basically the same thing. We're trying to push a little forward and help ChatGPT make the semantic gap a little smaller with frame semantics. So the difference now is that we did everything manually back then. So we have a bunch of students annotating all those images and going through all those captions. What we are trying to pitch now to the members of FrameNet Brazil is this idea of data layering automation. Because as we are going probably to discuss with data layer, is that the problem is like FrameNet only has like 1,600 or 1,700 frames, and we sure need to expand that to at least like 100,000 frames. And the problem is developing and maintaining a model using supervised machine learning requires huge amount of data. And training large language models on large data set creates several challenges, especially labeling the vast amount of data. So doing that manually to FrameNet is super time consuming and expensive because you have to pay people to do that. If you could find a way to make that automatically and just ask humans to validate the data, that would make the process faster. So the kind of data I'm working now is this. I got here an example. I'm working in Portuguese, but I got here an example in English so you can follow the explanation. But the idea is that you have on news articles, you have like a title, an image describing that presents what's happening in the title. You have some sort of broader description of what's happening over there. And the idea is that we get that data. And for the sentences, so for the text, for the text part, which is the title, we insert here, we run that through Loam. That is, you can use that. And it will automatically extract the frames that are evoked by each lexical item in the sentence you're providing, right? You probably see there's a problem here because high and school are two different things for Loam, but that's why we do validation, because sometimes like it was supposed to be high school and not high position on a scale and school a locale by use, it was high school. But apart from that, you have Loam automatically tagging all those items using FrameNet labels. And with that, you see that you have like people by age, for example, which was evoked, and you can also correlate that with the image. So you have, as you have in the frame, like, oops, you have age and person, which are the core frame elements. You have the person and the age. Or you can also have the social connection that they establish, which is an individual, and the type of connection that they have to each other. Or, for example, individuals and the connection. We also, differently from what we did when we were working with the multi-threaded data set, we are now trying not to use closed set object detection like YOLO or Amazon Recognition, which have like a limited number of classes for objects. So if you remember YOLO, you have like 80 classes like pizza, bottle, silverware. Instead of doing that, and even if you use like OpenImage P8, which has like 600 classes, that's also a limited number of classes. What we're trying to do now is using Ground Dino, which has a climate. This is a thing that was developed after I finished my PhD. That's why I didn't use it. But what it does is that you can ask ChatGPT, you provide the image, and you ask ChatGPT to extract the entity relationships, the scene description, the event description, a list of objects. And then you can get this output and you can use, oh, by the way, the running 1,500 images for that extraction took me like $3. So it's something that you can test at home. It's an expensive endeavor. But you can take the scene description and ask Groundino to use that to identify the entities in the image. Instead of using a closed set of classes, you can just show the description to Groundino and say, okay, I'm showing you an image, and this is the description of the image. Now go there, look to the image, and try to find what I'm telling you that it's in that image. So even if the model have never seen like a blue unicorn, if you tell the model that there's a blue unicorn on that image, it will look for the blue unicorn and will draw a bounding box. So you're not limited to the number of classes of whatever model you're trying to use for a computer vision. And so this is the script. I can send you the link for that one. This is the script you use to provide the prompt with the description, you provide the image, and it will give you the bounding boxes. We're finishing here. I have two takeaways before Q&A. The first one, and both takeaways are not related to the research I did, but for the way you're going to do your project. The first takeaway is, we're discussing this, like, keep in mind that this is cognition and computation, not cognition and computation. Because since you are students from computer science, it's tempting to brute force your way through the project, because you know the computational side of the project. So it's tempting to do that, but keep in mind that using the theory is also informative in what you're going to do. So if you're planning to use AI, I recommend Reclaiming AI as a theoretical tool for cognitive science, this paper. And also like Changing the World by Changing the Data, which discusses biases in data sets and how you can minimize the bias while developing tools for this. And I don't know if you know Research Rabbit, but if you pick up any paper that you know that you're going to need as a reference and you run it through Research Rabbit, it gives you a connection of all those papers that somehow reference that paper, or somehow are similar, or somehow have citations of that paper. So it's a great way to navigate papers and find new references for what you're planning to do and see what other people do in that same field. And finally, focus on making the monkey sing and not building a fancy pedestal. I don't know if you're familiar with the story of the monkey. No? So the idea is that we're discussing this, like the idea is that when you give someone the task of, so you have to train a monkey to sing on top of a pedestal. It's tempting to start building the pedestal and like getting the license for the song and buying the microphone. And then, okay, now I got the license and the monkey can sing Mariah Carey. Yeah. And oh, by the way, here's the pedestal. It's marble. It's beautiful. Yeah. But you're not moving forward. The problem here is training the monkey to sing. That's the hard part. So it doesn't matter if you have a pedestal and the license and the microphone, but yeah, unless you make the monkey sing, everything else doesn't matter, because you're not getting close to accomplish the task of making the monkey sing. So it's tempting to think, oh, yeah, no, I already have the pedestal and the lyrics and everything. Yeah, but by the end of the project, the monkey will not sing on top of the pedestal. So try not to focus that much on building the pedestal and figuring out if you will be able to make the monkey scene by the end of the project. So as Mark, like, try something small, and because you can iterate on that. So think about in terms of a minimal viable product and what's the smallest and easiest thing you can do in, like, I don't know, 10 weeks or 11 weeks that we have to finish this course. And that's it.